Alrighty, well, welcome to Module 4, Lesson 17, Mixture Problems. Okay, so we'll use some percentages to figure out some mixture problems. And when I say mixture, I literally mean mixture. Okay, so we are actually going into the chemistry lab, let's say, but actually not a chemistry lab quite yet, because we'll be dealing with we're dealing with juice first. Okay, so let's just take a look at this opening exercise, and hopefully this will clarify what we are about to do. Okay, so imagine you have two equally sized containers. One is pure water, and the other is 50% water and 50% juice. Now, if you combined them, what percent of juice would be the result? Okay, and as you can imagine, just you're thinking to yourself, and you have equally sized containers, and in this case we're going to do gallons. All right, it doesn't actually say it in that those opening lines, but as you can see on the table there, we're going to be looking in terms of gallons. If you have one that is pure water, okay, so let me just, I think I have a picture of that right here. Oh, there we go. Okay, so if we have one that is pure water, okay, and you guys have seen these gallon jugs of water before. We may actually use them when you go camping. We use them in the lab when we get distilled water sometimes, or purified water. Anyway, if you just imagine now, beforehand, we could just do a little prediction here. So if you have one full gallon of water, okay, and then you have this other bottle or jug, gallon jug, same thing, that is juice, like that, okay, but now in this juice, it's not all juice. Okay, it is only 50% juice, 50% water and 50% juice. So we could draw a line here. We have it's 50-50. Okay, there we go. So we draw a line there. It's just, this is the juice part, and here's some water. And of course, it doesn't separate out like that. But you could just imagine to yourself, what do you think the percentage of the juice will be in the combined resulting liquid, because that combined resulting liquid is going to be 2 gallons now, okay? It's going to be 2 gallons. Thinking to yourself, the one is 50% juice, and the other one has no juice whatsoever in it, okay? So you've got to think right away, maybe we're predicting that it's going to be less than 50%, okay? It has to be less than 50%, all right? So little prediction, something to check when we come to an answer, and if our answer doesn't jive with that prediction, we may have to rethink it or look at it again. Okay, so when we look at this this first liquid, so there's the first liquid, and there are the contents of that first liquid. Okay, there is 1 gallon right here of water. Okay, 1 gallon. Total, 1 gallon total. That's it right here. All right, and there is no juice in there. Okay, 0 juice. All right, we have our second liquid. Okay, which is a total 1 gallon. Okay, and there it is right there. That's our 1 gallon container. But it has 50% or 0.5 or 5/10 juice in it. All right. So if we're going to go ahead and figure out the percent that this juice comprises in this 2 gallons, what we need to do, of course, is we need to make a fraction. All right, because fractions are our friends and very, very helpful. And when we write a fraction, we write what we have, which is half a gallon, or 0.5 gallons, and what the total is, which is 2 gallons. So we have our total, which is the total liquid, which is 2 gallons, and then we're going to actually put the 0.5, which is the half a gallon. So we're trying to find out what percentage of, well, let me take that one back. What percentage of this is this? Okay? What percent of our denominator is our numerator, or what percent of the entire contents of this new jug is juice? Okay? And that would be 25%. 25%. If we take that 0.5 and divide it by 2, we get 25%. All right? So 25% of this resulting mixture will be pure juice. Okay? And there is a 2-gallon jug. All right? 2-gallon jug. So let's look at these 2 jugs again, just real quickly. It would make sense now if you look here. I've already split this one here into 2 parts because I know it was 50% juice. Okay, so 50% juice, which is down here, and then 50% water, which is here. Now this one, if I go ahead and split that in half, okay, split that into 2 parts, this is water and water. Okay, water, right? Because it's all water. All right, so I'm just actually turning these 2-gallon jugs into equal fractions in a sense, right? And it makes sense that 25% is juice, because look at this. There's 1 part, or 1/4 juice, so that would be 1 over 1, 2, 3, 4 total parts, or 4 total fourths. Okay, and that equals, of course, 25%. Okay, so you can see these problems can be tricky, especially when you have lots of words and you don't know what to do with what, but it does indeed make sense, especially when you look at it as a picture. It really makes sense. Okay, let's go ahead and see how much sense it does make, and let's try another. All right, so now if a 2-gallon container of pure juice is added to 3 gallons of water, what percent of the mixture is pure juice? So here we go. We have some numbers to work with. Okay, and again, we're going to divide that into 2 different liquids. Okay, we have liquid 1, liquid 2, and then the resulting liquid. Okay, it's actually 3 different liquids. So let's go ahead. So if we go ahead and plug these numbers in, we have a 2-gallon container. Okay, and we'll call that liquid 1. Okay, pure juice, and then a 3-gallon container of water. All right, so as you can see here, the pure juice part, that first liquid is 2 gallons, and it's 2 gallons of pure juice. Okay, 2 out of 2, so we could see right there that it's 100% juice, right? 100% juice here. Okay, but now we have the liquid number 2, which is 3 gallons total, and it's only water. Okay, so this is actually 0% juice here. Okay, now we're going to we can look at it several ways right away. Maybe some of you are looking at it and saying, "Hey, well, I have a total of 5 gallons of liquid, and I have 2 gallons of juice total." Okay, I could very simply do, and I think I did do this already, 2 over 5, which equals 40%, and that's exactly how we do it. Okay, exactly how we do it. You have your resulting liquid, the total. Okay, what part of that, what fraction of that resulting liquid is juice in this case, because that's what we're looking for, and that's 2. Okay, that went into it. So 2 out of 5 is 40%. Okay, so 40% of the resulting mixture will be pure juice. Okay, pure juice. And the rest, so 60% is going to be water. So both of these are watered down pretty much the first one was a lot more watered down than that second one. Okay. All right, so we have a next one, another scenario. Now, if we have a 2-gallon container of juice mixture that is 40% juice and added to 3 gallons of water, what percent of the mixture is pure juice? Now, again, we can look at some numbers here. We have a 2 gallons and 3 gallons, so we know we have a resulting liquid total is going to be 5 gallons again. But in the first scenario, those 2 gallons were 100% juice. In this case, we're looking at 40% juice. So right away, you might be thinking, and you might be correct in thinking, that the percent of juice in this last mixture is going to be less than 40%, okay? Because with 100%, 2 gallons of 100% juice, you ended up with a 40% total in the resulting liquid. Therefore, it would make good sense that it would be less than 40%. Okay, let's go ahead and see. Let's plug some numbers in. Okay, those numbers are the same as the one that came before because we have those same containers, a 2-gallon container, a 3-gallon container, and resulting liquid is going to be 5 gallons. All right. So now this first, the amount of pure juice, all right, is 40% of the 2 gallons. Okay. So we can look right here, and if we take a look at these words, we have, and we've done this in the past, just in different situations. Okay, so we have 2 gallons and 40% pure juice. So 40% of that 2 gallons is juice. Okay, pure juice. All right. Therefore, we know we have our of. All right, and we know we're doing multiplication. So that's what we do. We do our 2 gallons times that 40%, and that's going to equal 0.8. Okay, so 0.8, or 8/10 of a gallon. Okay, so less than a gallon even is pure juice. All right, and then we know second liquid is, again, just water, no juice at all. And as you can see right now, we have less juice in the same total amount. Therefore, as expected, we have a lesser percentage of pure juice in that resulting liquid, okay, because we only have 0.8 or 8/10 of a gallon divided by the total 5 gallons, resulting in a 16% pure juice mixture. Okay. So hopefully that was a good warm-up. Hopefully that made it a little bit easier to understand. Actually, sorry, it's not over yet because we do have another juice problem. Okay, and here it is. Okay. Now we have a 2-gallon juice cocktail that is 40% pure juice is added to 3 gallons of pure juice. What percent of the resulting mixture is pure juice? So, unlike the others, it looks like we might have a little bit, or maybe quite a bit of more juice in the resulting liquid, because, as we see, we have, instead of 3 gallons of water in that second container, we now have 3 gallons of pure juice. Okay, so we can see there's quite a bit of pure juice going down this time. Okay, again, same amount of liquid, 2 gallons in the first one, 2 gallons in the second, 3 gallons in the second, then 5 gallons total. Okay, that resulting mixture is going to be 5 gallons, but very different numbers otherwise. Okay, still that first container still has that 40% pure juice mixture, so it is going to yield 8/10 of a gallon of juice. But that second one has 3 full gallons. It is pure juice. Therefore, it is 100% juice. So we now end up with 8/10 plus 3. So 3 8/10 of that 3 8/10 gallons of that resulting liquid is going to be pure juice. And of course, we divide that by our total gallons, and we end up with 76%. So the resulting mixture contains 76% pure juice. Okay? I like nothing other than 100% pure juice, so I won't be drinking any of those, and neither should you. Okay, so that was a good warm-up. You can see how similar amounts of liquid can result in different mixture percentages based on what goes in it. And that probably makes good sense to you, I'm sure. Okay, so here we go. Now we have some trail mix. All right, so we're dealing with food. I guess we're in the kitchen before we go into the chemistry lab. A 5-gallon container of trail mix is 20% nuts. And boy, that is a lot of trail mix. So here is a picture of a 5-gallon bucket, and I'm sure you've seen those before. Sometimes if you're painting a house, you get a big 5-gallon bucket of paint. If you're painting the whole outside of your house, could be a couple of those to paint your house. But anyway, just to give you an idea of what 5 gallons, a 5-gallon container of trail mix would look like. Okay, that is a lot of trail mix. Anyway, let's get back to this here. So yeah, a 5-gallon container of trail mix is 20% nuts. Okay, another trail mix is added to it, resulting in a 12-gallon container of trail mix that is 40% nuts. Okay, so unlike the problems that came before this one, okay, we now know something about the end product. Okay, with the resulting, we have 12 gallons of 40% nut trail mix. All right, so here is the trick. What I want you to do, and I want you to pause and go ahead and write an equation to describe the relationships in this situation. Okay, so I'll give you a hint. What plus what equals what? Okay, so go ahead and give it a whirl. Come on back and use what we've done before and what you've done prior in other lessons, and do your best to persevere. Come on back and we'll check it out. Okay, so go ahead and pause. Okay, so let's see how you how you did and how I did, how we did. Okay, and again, the idea here was to write an equation. Okay, we're just writing an equation right now. All right, and we have some different parts here. All right, we have 5-gallon container with 20% nuts, and we've got a final 12-gallon container that is 40% nuts. Okay, so let me probably got to move my move my little pail here. Excuse me. I'm going to select my little pail. No, I'm not going to. Can't select my pail. Anyway, what is behind that pail? I will tell you right now, because I just added this pail at the last minute. Was our famous Q equals P times W formula. Okay? All right, so if we are thinking in those terms, that will help us out. Okay? So now, the resulting 12-gallon container of 40% nut trail mix. That's how that would be expressed. Okay? Because that is, and again, that's going to be our Q here. Because remember, our Q was the result of something. Okay, it was the result of something, some quantity that was a result of applying a percentage, the P, to a whole of some sort, or an original quantity, which was W. Okay, so the 12 times 0.4 is our resulting 12-gallon container of 40% nuts. All right? Okay, so next we have a 5-gallon container of trail mix is 20% nuts. Okay, so we've got to add that with something else, of course, to get the resulting 12 gallons of 40% nuts. Okay, so this right here represents this container right there. Okay, now the next part. Okay, the W, I'm sure you understand where that came from. That is our unknown, okay, because we don't quite know the percent of our, I put W there just for as an unknown, okay, but that doesn't actually stand for the whole, so that might be a little bit misleading. Let's go ahead and make that P actually, because that would make more sense, because that is a percentage there that we're looking for. Okay, that's a percentage there that we're looking for. Now you might be asking where the 7 came from, though, okay, because that's a bit of a mystery maybe. But it doesn't need to be a mystery, because if we know we have a resulting 12-gallon container, and we have 5-gallon container we already know about, it's very simply to say, well, I know I end up with 12, and I know I have 5 in one container. What's in the other container? 7. Okay, so that's where that 7 comes from. That's another 7 gallons of some mystery percentage, okay, because I don't know what that percentage right there is, okay? All right, so let's go on. The next thing, or, okay, 12 minus 5p, okay, 12 minus 5p. And the reason I put 12 minus 5p, because it's a little bit more explicit. It tells you what numbers I was using, okay? Of course, 7p is the result of 12 minus 5p, but just to be more explicit about where I got that, that 7 from. Okay, so now we're going to explain in words how each part of the equation relates to the situation. We could do so like this. The 12, or the 12 times 0.440 represents the resulting mixture. And again, I've said this many times already, but I'll continue. The next part, okay, the 5 times 0.2 represents the 5-gallon 20% nut mixture. And finally, that 12 minus 5p stands for the amount of the unknown multiplied by the unknown percentage, okay? So, and the unknown, I guess, quantity, I meant to say right here. Should have put there, quantity. All right. Well, in a sense, it's unknown until we just do the subtraction, I guess, right? Okay. Now, finally, what they want us to do is they would like us to figure out what percent of the second trail mix is nuts, okay? Because that is what is unknown, and that's what sits right here, this P right here, okay? So let's go ahead and do some magical algebra. Here we go. So what I've done right there is that 4.8, that is the result of here, multiplying my, oh, hold on a second. Whoopsie daisy. Let's go back. Okay. That, again, that 4.8 is a result of my multiplying my 12 times 0.4, okay, and that gives me my 4.8, okay, so I'm working across from my equation up top, okay. And then my 1 comes from the result of 5 times 0.2 is 1, and then of course I have my 7p, which is a result of just working out that parenthetical there, okay? And here we go, and you know what to do, and this has been, again, maybe, well, not long ago, but we continually are doing our algebra. We learned long time ago about how we isolate variables, and that little pesky 1 over there next to that 7p needs to be dealt with, and you remember how to deal with it. Subtract it away, okay, or add its additive inverse, okay, and what we the result is, of course, and again we have to subtract from both sides of the equation. So now we have 3.8 equals 7p, which of course is 3.8 divided by 7, or of course multiplied by the multiplicative inverse of 7, okay, just to isolate that p. And further, if we figure that out, if we put that into a computer, calculator, which is a form of computer, I guess, 3.8 divided by 7 equals 0.5429, which we could round to 54%. So the resulting mixture of trail mix, actually that's not right, it's not the resulting mix, it's actually the second trail mix turned out to be a 54% mixture. It was 7 gallons of 54% nut trail mix. Okay? Alrighty, so let's proceed. And again, if some of this is coming and going, slipping, going in one ear, going out the other, just go back, look, slow down, give me a call if because some of this starts to move a little bit quickly towards the end of this lesson. It gets a little bit more difficult, but we'll only have one more lesson after this one, actually, to complete topic C. So I don't want to leave you hanging if there are questions. So please do call or email me with any question you may have at any moment. Okay. All right. Here we go. Next is exercise 1 here. It says represent each situation using an equation and show all steps in the solution process, okay, which is real important and something I want to continually emphasize. Haven't been checking this much in your, well, actually at all in your binders, but I do hope and I do trust that you are all being very diligent about showing your steps in the solution process, because that becomes more and more important as you move through algebra. All right, here we go. Here are the facts. We have a 6-pint mixture that is 25% oil. Okay, let me go find a picture of a pint container. I'll be back. Okay, so here we are back again. Okay, so I wanted to show you these pictures here. I thought this will help. It's a good, I like this illustration here. Again, nothing is filled up in its entirety, but really good example. So here's our gallon. It's a gallon container right here that we've been using. We've been talking about. Okay, that's a gallon right there. Just to show you what these look like. And again, I know some of you this may seem insulting, because I know you know a lot of this, especially those of you who help around the kitchen. Okay, here's a half a gallon here. All right, and then we have a quart. Okay, right here, and then here's our pint. That would be a pint, the blue liquid there, and this is a cup right there. Okay, all right, and in terms of ounces, of course, or in terms of the way those are, they compare. Okay, you have 1 cup right here, 1 cup. This here is going to be 2 cups. Okay, and this is going to be 4 cups. And this is going to be 16 cups. Okay, and this, of course, would be 8 cups right there. All right, so you can see that a pint right here is 2 cups, which is 16 ounces. And again, I don't know if much of this means anything to you. I won't go into all these quantities entirely, but it is good to actually see what exactly we are we are working with. Okay, so before, when we were talking gallons, oops, boink, we were talking gallons, we were talking about these big ones. Now right here with the pints, we are talking this one here, those are pints. So 6 of those actually would be one of these, and then another 2 of these. Okay, no, wait, hold on a second. Is that right? 6, 2, 1, no, 2. Actually, no, it would be 3 of these. Hold on a second. Okay, so 6 pints would be actually 3 of these quarts. Okay? 3 of those quarts, as you can imagine. So 6 pints is not going to quite be a gallon. Okay? Not going to quite be a gallon. All right? So anyway, yes, that's what we're working with right now. But let's just continue. Sorry, this is taking long. Don't want to take too long. All right, so anyway, we have a 6-pint mixture that is 25% oil, and it is added to a 3-pint mixture that is 40% oil. Okay? What percent of the resulting mixture is oil? Okay, again, just different liquids, but a similar process to what we've been doing already. Okay, so what I'd like you to do, therefore, is to use what you have already done or already seen, and I will pause. You work it out, and come on back and check in. Okay, let's see what you did, where you started. Here we go. I am going to go ahead and employ again. Sorry, let me get rid of this one. Going to employ our Q equals P times W formula again. All right. And I'm going to start with 9Q because Q is that quantity that is the resulting quantity. Okay, remember that Q is the result always of some whole or some original amount multiplied by a percentage. Okay, so we don't know exactly how much, but we do have 9Q. Okay, we do have 9Q. We don't know the percentage of but we do have 9 pints that we know of. Okay, so 9Q equals 6 times 0.25, which is a 6-pint mixture that is 25% oil, okay, plus a 3-pint mixture that is 40% oil. Okay, so when we're working with these with these equations, and we have to make a few things even, and these right here need to be even. So 9 has got to equal 6 plus 3, okay, because we have 9 pints, so we have to have the 6 and the 3 have got to equal the 9, and that's where that 9 came from. The 9 wasn't shown anywhere in the problem, but it is a result of the 6 plus 3, okay? All right, so again, we're just moving along here, and I'm doing my multiplication, and I have now that 9Q equals this 1.5 plus 1.2. All right, 9Q equals 2.7. I guess again, I'm just doing my algebra. All right, and again, as you know, with my 9Q, I need to isolate that Q. I'm going to divide that by 9, and I'm also going to divide my 2.7 by 9. And therefore I get Q equals 2.7 over 9, or 0.3, or 30%. So what does that tell us? Well, that tells us that the resulting mixture is 30% oil. Okay, 30% oil. That resulting 9 gallons, sorry, not 9 gallons, hello, stop it, 9 pints of oil is 30%. 9 pints of liquid is 30% oil. And again, I don't know what the other part of it is. They're not telling us that. It's surely not water. Okay, and you guys know why? Might not be water. Probably isn't water. That's right. Water and oil don't mix, and they're very, very different densities. Therefore, oil floats on top of water. Okay. Let's continue. Yes, we're getting sciencey here. Okay. And our next one, we're going to talk about some gold. Yes, everybody's favorite metal. Well, maybe not exactly everybody's. Yeah, so we have an 11-ounce gold chain of 24% gold. Was made from a melted down 4-ounce charm of 50% gold and a golden locket. Okay, so let's go ahead and look at those numbers and such again. So we have an 11-ounce gold chain of 24% gold. Okay, that is, because you can see made from, it was made from, therefore we can get an idea that that 11-ounce gold chain of 24% gold is going to be our resulting mixture, or resulting product. Okay, and it was made from a melted down 4-ounce charm of 50% gold, one of the ingredients, and a golden locket. Okay, and as you can tell, that golden locket is an unknown. Okay, we know it's gold, all right, but we're not getting any percent of gold, and we're not getting any weight of any sort. Okay, so what we are being asked is what percent of the locket was pure gold. Okay, so again, this is very similar to actually not the one above, but the one before that in terms of uncovering the actual weight of the golden locket. All right, but go ahead. I would like you to go ahead and tackle this on your own, and come on back after you have promised me you have persevered. Pausing now. Okay, we are back. Let's go see here. Yes, Q equals P times W. And again, hopefully these Q's and P's and W's aren't throwing you off. I'm just using them because I just want you to see how related all this percentage stuff is. Okay, so my Q, again, like we had talked about, like my gold color there, my gold circles. Anyway, like I had kind of hinted at when we first started reading this problem, you could see that 11-ounce gold chain of 24% gold was going to be our resulting product, because it was the product that was made from. Therefore, it's going to stand as our Q. Again, it's 11 ounces. All right, 11 ounces at 24% gold. Okay, or 0.24. Okay, equals. We know we have a 4-ounce charm of 50% gold. Okay, and we're going to add that to. There we go. I got a 7P. Okay, the P is going to be that percentage that we don't know and that we're solving for. Okay, where did I get the 7? All right, hopefully you know. If I know the resulting gold chain was 11 ounces, and my my charm was 4 ounces. Then, of course, the locket, which wasn't given to me, but I'm able to figure out, is 7, because 11 minus 4 equals 7. Okay? All right, so again, just working my math here with my calculator or freehand or whatever, just calculators are fine. Okay? As long as you are, the process is, you've got the process down, you got the lingo down, you know the big picture, calculators fine. So 2.64 equals 2, and that 2 came from 4 times 0.5, because half of 4 is 5. I mean, half of 4 is 2. Duh. Anyway, so there we go. And just working it out, again, I got to get rid of that 2 on the right side. Okay, this little pesky 2 here, because we need to leave that P on its own. Subtract away that 2 from both sides. Ooh, boy, I went fast with that one, didn't I? Okay. So when I subtracted the 2 from the 2.64, I got 0.64 equals 7p. Okay, and again, I'm going to isolate that p, and by dividing it by 7, and also 0.64, divide that by 7, and we get 0.0914, and I'm only going out to the 10,000ths place there, okay, because that does go longer, and that would equal roughly, or round that to 9%. So the resulting, I'm sorry, the locket of gold, okay, the locket, that 7-ounce locket was actually made of 9% pure gold, okay, 9%, not very much at all. Okay, so I just flipped that. I'm not skipping a problem. It was just that's the same problem that was underneath that other one. It's just we need some room. Okay, so now we have finally gotten to the science lab. Okay. Now in the science lab there are 2 containers that are filled with mixtures. Yes, that first container is filled with a mixture that is 30% acid. Wow. This is really, really dangerous science, okay? Yes, 30% acid. The second container is filled with a mixture that is 50% acid, and the second container is 50% larger than the first. Ooh, that's a little curveball we've thrown in here, huh? Okay, so we'll work that one out. Don't worry, don't fret. We will get through it. You'll get through it with me. Hopefully, in the near future, you'll be able to get through it all by yourself. If you're not able to already, because you might be, okay? All right, so the first and second containers are then emptied into a third container. What percent of acid is in that resulting third container, okay? And you can notice here what we are missing, a big glaring missing piece is, of course, any mention of an amount, such as milliliters, because milliliters are liters, because those are actually the liquid measurements we work with in a science lab. Okay, but how do we get around that? Well, why don't you ponder that a little bit, okay, and come on back after you have pondered, scratched your head a bit, talked it over with mom or dad or sister or brother or friend, and come on back with your ideas, or maybe with the problem completed. Okay, so I'm about to pause now. Okay, we're back. Let's see how you did, what you did. I'd love to hear your ideas, but as I can't, we will continue. Okay, so we will need variables as we have no amounts to work with, okay, or with which to work. Okay, more of a proper grammar there. Okay, so which container is best to use as our reference? Okay, that would be my question to you. I'd love for you to think about this a bit. Which container is best to use as our reference after reading through the problem again? Okay, well, let's go ahead and let M equal the first container, because, as you can see right here, they have compared the second container to the first container, saying that it is 50% larger. So whenever that is the case, whenever one item is being compared to another item, it's usually that other item that we're using as our reference, or as our whole, or as our W, as we use in our Q equals P times W equation. Okay, so let's go ahead and let M equal our first container. Okay, so this means 1.5 M is our second container. So I would ask you, if you were here, why? Why do you suppose I have chosen 1.5 M as the second container's representation? Well, if we look at it, if it is 50% larger, okay, if it's 50% larger, that means I have to account for it, for the whole of M, which is 1, and then 0.5, which is another 50%. So 1.5 M is our second container. So that's something we've talked about quite extensively in lessons prior. Okay, so we can go ahead and start putting our equation together. This first container, M, contains 30% acid. Therefore, we have our 0.3 m. Okay? We are going to add that to 0.5 times 1.5 m. Okay? Because our 1.5 m is our second container, but we have to account for the 50% acid that it contains. Okay? And that's where that 0.5 comes from. And that all equals the third container acid content. Okay? The third container acid content. So this is not exactly Q. Well, it is kind of Q equals P times W in a way, but a little bit different. But anyway, as you can see, I've made a very convenient equation out of it. So what I'm going to do here, therefore, is I'm going to add those up. So I have 0.3 m. I don't need to mess with that at all. But now I have to multiply 0.5 times 1.5 m, and that results in 0.75 m. And if I add those two together, I get 1.05 m, okay, 105% m, in other words, is equal to the third container acid content. Okay, so that's just the acid, all right, just the acid. Now, you might be able to guess, or I would ask you if you were here, what else do I need? So I have my acid content in the third container. I'm representing it as 1.05 m. What else do I need in order to answer that final question, which is what percent of acid is in the third container? Think about that. Ponder that a little. Okay, well, what I need is I need the actual container amounts. And again, I don't have them, but we have represented them. We've represented them as m and 1.5 m. Okay, that's the total contents of those containers. All right? So if we have those, we add those together, and we get 2.5 m. Okay? And this is where some of this gets a little bit confusing, maybe, okay, because now we're using variables in very creative ways. So what we've done is we've taken, we let m equal that first container, and we let 1.5 m be the second container because it is 50% larger, and that is going to actually represent the total of the contents. Okay, again, it has no real value as it is. We'd have to plug in a number for m to actually get a real value, but we have to represent it some way. Okay, so that's going to be that whole. That's all of the liquid we have. The acid content is going to be represented as 1.05 m, okay, which we put on top there because we're trying to find out what percentage of 2.5 is 1.05, okay? And if we do that, we get 0.42 or 42%. So the answer to this question right here, what percent of acid is in the third container, is 42%. Alrighty, we are getting close to 50 minutes, so I want to try to buzz along here. All right. So here we go. We have some soil. All right. Soil that contains 30% clay is added to soil that contains 70% clay to create 10 gallons of soil containing 50% clay. All right. Question: how much of each of the soils was combined? Okay, so now we are trying to solve for how much of each of the two soils was combined. Well, what do we know about these two soils? Well, we know the first one was 30% clay, second one was 70% clay. That's all we know about those two soils. But we do have some very important information. We know that we have 10 gallons of soil total at the end, and that soil is a 50% clay mix. Okay, so go ahead and plug in these numbers. based on other problems we've done, and come on back and check how you did. Okay, well, let's check it out. Okay, so another variable needed. Okay, so we need another variable, all right? In this case, we're going to go ahead and let's say the first container is X, okay? The first container is X, and that's that soil that contains 30% clay, okay? So the first soil amount times the percent clay plus the second soil amount times the percent clay equals the resulting amount times the resulting percentage of clay, okay? And this part right here we have in its entirety already, okay? We have that already given to us, okay? But some of those other parts we are in need of, okay? So let's go ahead. So our first soil amount, we're going to say, we're going to let it equal X, okay? So there it is, it's X. But we know already that clay percentage, okay, so we'll go ahead and plug that in. So we have now represented our first soil amount and percent clay as 0.3x, and we're going to add that to the 0.7, which is the 70%, which is the clay percentage of the second soil. And but what are we going to put in there? And this is going to be, this is our first unknown here. What is that second soil amount going to look like? What do we know about that second soil in terms of its amount? Okay, the amount we've applied to the first soil is plain and simply X. Therefore, we are going to compare this amount of soil to the X. Therefore, you know X is going to be in there somewhere. Okay. But what do we know about the entire amount of soil? We know that it's 10 gallons total. Okay, 10 gallons total. So what goes in these parentheses right here? How are we going to represent the amount of that second soil? Very simply, 10 minus X, okay? Because we know we have 10 in the end, and we're representing the first soil as X. So we got to take what we know, that 10, and subtract away the X, okay, which again is an unknown. And some of this, it gets a little weird. I know it does, but well, I'll tell you, it looks a little weird, and it sounds a little weird when you say it. But hopefully, it's making sense to you because it's really exciting when it does. Okay, so that equals, and again, we have 10, 0.510, which is a 50% clay, 10 gallons of 50% clay. All right. So again, here we are. Now the only thing that's left to do here is go ahead and do our algebra, all right? So 0.3x stands the same, but with the next expression, that 0.7 times 10 minus x, we need to work a little distributive magic, right? So 0.7 times 10 equals 7, and then 0.7 times negative x, very important, okay, is negative 0.7x. All right, so we've used distributive property, and that, of course, equals 5, all right, because 0.5 times 10 is 5, same as a half times 10. All right, and okay, so here we're going to do is continuing our algebraic process. We have some like terms to combine, and those like terms are that 0.3x added to a negative 0.7x, okay, and that of course is going to give us a negative 0.4x, okay, plus 7 equals 5. We got that pesky 7 in there. Got to get rid of that. We need to do it on both sides. Now you'll notice this is a weird looking, very ugly kind of situation at the end there. We have a negative 0.4x equals a negative 2. Well, when you have negative values on both sides like this, you can just go ahead and eradicate those negative signs. Okay, you don't need them, okay, because they're both on the same. If they're on the same side, we could just go ahead and take those away. All right. So, and again, just to continue our algebraic process, to isolate that x, or create a 1x there, we need to divide it by 0.4 and do the same on the other side. So that 2 divided by 0.4 is 5, and therefore x equals 5. So what exactly does that mean? What is that x? Well, I should go back. I don't want to do that yet. Oh man, hold on. Okay. What is that x? Well, that x, of course, would go right back to the beginning here. And right here, that x was our first container. Okay? So we know that our first container is 5 gallons. Okay? And if we know that our first container is 5 gallons, we have a total of 10 gallons. That means we have 5 gallons of each soil. And that was our question. How much of each soil was combined? Right there. And our answer is 5 gallons of each. Alrighty. Let's move on. Okay, this one I know it looks really long. It's not. These questions are pretty straightforward. Okay, I'm going to get done in less than an hour. And here we go. Okay, so now we have an equation. Let's take a look at this equation. 0.2 times x plus 0.8 times 6 minus x equals 0.4 times 6, and that is used to model a mixture problem. Okay, this is an equation that's used to model this mixture problem, and these are things that we've been creating, equations like this, during this lesson. Okay, so what I want you to do is I want you to go ahead and take your time, make sense out of this, answer A, B, C, and D, and come on back and let's check in. Whichever ones you're a little bit confused about or don't know about, you can skip and we can do them together here when you come back. But I would like you to try to persevere because I think you can indeed answer most, if not all, of these yourself. Pausing now. Okay, we are back. All right, the first question was how many units are in the total mixture? Okay, so if you look at our that equation, we have a 6 there, and we have 6 units. Okay, because we know our total mixture is going to sit on the side by itself on one side of that equation, and that is 6. So we have 6 units total. What percents relate the two solutions that are combined to make the final mixture? Okay, so we're looking for the percents, and again, these are the two that were combined to make the final mixture. Okay, we know that by now. We know the final mixture is sitting on that right side of the equation, but which of those figures there represent the percentages? And I think you probably got this right. The 0.2 and the 0.8. Okay, 0.2 equals 20%, and 0.8 equals 80%. Okay, next, what the two solutions combine to make 6 units of what percent solution? Very simple. We can look at there. 0.4 sits in front of that 6 units. Therefore, we know that is a 40, stands for a 40% solution. Okay. Finally, it asks us when the amount of a resulting solution is given, for instance, 4 gallons, but the amounts of the mixing solutions are unknown, okay, which is, in this case, how are the amounts of the mixing solutions represented? Okay, how are they represented? Well, the amount of the resulting solution is given already, okay? The amount of the mixing solutions are unknown. Okay, the first mixture, or the first mixing solution, can be X. Okay, if you want to do it that way, you can make it that way, whichever makes sense, or whichever, and it depends very often how they're making their comparisons. Okay, but we could make the first mixing solution to be X, and thusly the second solution is 4 minus x. Okay, in this situation, 4 minus x, simply because we know that the total resulting amount is 4 gallons. Therefore, the second one is just going to be that 4, take away the first one, which in this case is x. So x and 4 minus x. Okay? All right, here we are. I'm sorry we're going to go over an hour, but hopefully it's worth it. All right, so here we go. Lesson summary. Mixture problems deal with quantities of solutions and mixtures. The general structure of the expressions for mixture problems are this whole quantity equals part plus part. Okay, we did that a few times, and we also used our Q equals P times W. All right, but in terms of mixtures and solutions, there's always parts, always pieces. Okay, in this case, we only talked about two-part solutions or mixtures. Okay, so using this structure makes the equation resemble the following. So we have the percent of the resulting quantity times the amount of the resulting quantity, and in this case, this whole thing together would equal our Q that we used to talk about, or we still talk about, equals the percent of the first quantity times the amount of the first quantity plus the percent of the second quantity times the amount of the second quantity. Okay, so we have a couple P's and W's there, I guess, right? Okay, well, that's it. I've gone over by 2 seconds. Oh gosh, oh my gosh, over a minute, over an hour. Anyway, I hope it was worth it. Any questions, please call me. Good luck with your problem sets.